Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in 8th week and this is our first lecture. In this week, we are going to cover the design of staircase and flat slab. Our first topic today is the staircase design. Now, staircase is very common to us. It serves a basic purpose. As you all know, it is a means to travel or move from one level to another level. As you can see the staircase here. So we move from say ground level to first floor, okay, in a multi-story building. Now there are different types of geometry that we'll cover in a minute, but one thing is for sure, this is the most common structural element very often we see in different buildings, right? Now, the location of the staircase is very important because it should receive adequate light and ventilations and it should be accessible from different part of the structures. So, this point should be remembered while overall planning a structure because the architectural planning will place the staircase in the overall position within a structure, so that for normal operations as well as for emergencies, people should easily access this means to move from one level to another level. Now, width of staircase is extremely important because that provides safe passage from one level to another level, right? So, depending upon the type of structures that we are going to design, this width may vary. Now, for public building, obviously, we should provide space for heavy movement and therefore those stairs are wide compared to residential buildings. Now, for residential buildings, generally, we have a typical design and also for public buildings. So, as you can see, the width normally 1.5 meter to 2 meters for public building, while for residential building, it may be little less, roughly around 1 meter. Now, beside width, the length of the flight is also important. We cannot have a long stair that is uncomfortable for climbing. So, when we design the stair, not only the structural design, overall geometric design that you will see in a minute is also equally important. As you can see here, we have a stair which has two parts. So, in each part, we have number of steps. So, we divide it into two. So, in the first flight, we have certain number of steps and we have another flight where we have, in this case, equal number of steps. Sometimes there are other geometries where we have, say, 3 different flights and we can reduce the number of stairs or steps per flight, just to provide a comfortable movement from one level to another level. Now, normally there is a thumb rule that each flight should have a minimum 3 to maximum 12 steps. So, when we design geometry of a stair, we should keep that in mind to design the number of steps in particular flight. There are some other requirements also. Pitch of a stair. Now, as you can see here, this stair is moving this direction and there is a half landing here, and from this half landing again it moves towards the next floor. Now, when we design this, we should keep in mind that this angle is extremely important. It should not be steeper, it should not be flatter. So, we normally design stairs between 25 to 40 degree, right? That provides a very comfortable movement from one level to another level. Now, headroom is equally important. In a building, if we design, say, a frame, say this is a frame, and normally for residential buildings, these frame heights are 3 meter. So, this is 3 meter. So, if we provide a stair, say within this structure, there is a stair So we can provide a half landing here and then a stair there. So in that case, this stair covers the entire height, but we should provide clear vertical distance between the tread and soffit. As you can see here, if we need to enter from this place, so this is the height because this is the half landing. So this is the height. So we should keep sufficient space for movement. Now, normally there is again a guideline of 2.14 meter. So when we design that, we have to keep all these factors in mind. And then comes the material that we use for stair. In our case, we are going to use reinforced concrete. So we will have cement concrete plus steel rebars. With the help of those materials, we will design. But these stairs are extremely important during emergencies. So we should not use some additional materials. For example, you can see here we have railings, we have side panels for decorations. So those materials should not be inflammable, particularly during emergencies in case of fire. That may be risky, and that's why we should avoid using any such material. Beyond that, there are some other requirements also. For example, these railings are extremely important for safe movement. So we should provide that. Then this landing, as I have already explained, that it's better to provide a landing in between rather than having a single staircase. Then there are other requirements, but from structural point of view, the most important one is this one, step proportions. So as you can see here, we have steps like this. So when we design a stair, we should keep in mind the design of each and every step. It should not be too high and it should not be too flat. Normally, all the steps will have the same geometry. We should not vary that in a single flight. And for a particular tread and rise, also there are some standard guidelines that we should follow. What are they? They are here. So as you can see, this is what we call the tread or going, and this is the rise. So the most important guideline for the design of tread and rise is here. Sometimes we call going in place of tread. So going in millimeter plus 2 times rise should be 600 millimeter, and tread or going times rise should be 4000 to 4200. Now for a commonly adopted stair size is 300 millimeter going and 150 millimeter rise. Now we can reduce the going by some amount. As you can see here, if we reduce by 25 millimeter, we have to also adjust the rise by 12 to 13 millimeter. Right. Now, not only that, in case of residential building, we prefer the size of rise between 150 to 180 and the tread or going between 210 to 230. For public building, obviously, this going is slightly more, so it is between 250 to 300, and the rise is between 140 to 150. So these are some standard rule. We can stick to them and design a comfortable stair. Now, before we see the design of stair, let us see what are the different types of stair that we may encounter. Obviously, first one is a single stair. So if this is, say, the ground level and this is the first floor level, we have a single flight starting from the ground floor level to the first floor level. So this is a straight stair. Then comes the most common one, dog-legged stair. We'll actually design this type of stair where we have 2 flights. So this way you go up then there is a half landing here. So you turn and then there is another flight. So you go upstairs. So this is the side view from one level to another. This one is the most common one, and there is another modification of that, as I already told you earlier, that you can readjust the number of steps and you can introduce another flight at the mid-level. If that is the case, we have a open well stair, as you can see here. So you can go this way, then there are some additional steps here, and then finally you go to the next level. So because this open space here in between, this is called open well stair. Now it can have 3 flights, it can have 4 flights depending upon the design. Then there are geometrical stair. As you can see, it may be semicircular or other geometries based on the architectural design. Then there are circular stairs. These kind of spiral stairs are very common. And of course, the bifurcated stair, as you can see here. So there is a flight here, and from the mid landing, you can go either way. So this is a bifurcated stair. Now, out of all these possibilities, the most common one is the dog-legged stair, and in our design, we'll actually focus on this type of stair. So before we move into the design, let us see how these dog-legged stairs are supported. As you can see here, we can have the slab. This is basically a slab. As you can see here, this is a concrete slab with steels embedded. Then this slab can span in 2 different directions. As you can see here, the first one is here. Here each steps are supported by the walls on the either side of the stair. So this is what is called horizontal spanning. So for this, each slab acts as a beam supported at the 2 ends, and we can easily design this. There is another way you can support this stair at the ends, as you can see here. So from this spot, it goes this way, and then finally there is a landing here. So at the 2 extreme end, here we have one support and here we have another support. This type of slab is called longitudinally spanning stair slab. Now, for horizontal spanning, obviously the supports are at the 2 ends. So this is a beam which is supported at the 2 ends. It may be simply supported if this is a brick wall, or it may be fully fixed at the 2 ends. Accordingly, we have to design, but effectively this is a beam, and we can easily calculate the dead load and live load on this stair, and then accordingly we can find out the maximum bending moment depending upon the boundary condition that we use, and then as a beam design we can design this stair. So it's not a problem, it's as good as beam design, no additional requirement. But the question is, when the stair slab spans longitudinally, then how to design it. So we'll have one support here, another support there. Now as you can see in the cross section, the total depth of the slab is capital D, and you can see the trade and rise. This dimension is B, the width that we can actually find out from the geometry, that is rise and trade. So from the Pythagoras theorem, you get B is equal to square root of R square plus T square. Now, when we calculate the bending moment, for this we have to consider the load of each and every step, and accordingly we have two supports here and there. So we can consider it as a beam supported between 1 and 2, but while calculating the load we have to be careful to consider the weight of each step, which is distributed over this length. Otherwise, these steps are monolithically cast, so it is a part of this slab, so we can identify the capital D from the geometry. As you can see here, this is nothing but small d1 plus RT by B, which you can easily derive. So before we design this slab, the first thing that we have to keep in mind is the geometric design, and from that geometric design we have to find out the net load acting on the slab. The moment we do that, we can easily design this as a beam supported between the points 1 and 2. However, this slab is obviously inclined, so accordingly we have to take the load in our estimation appropriately. Now the first question is then, what is the span, effective span of a longitudinally spanning slab? It is given in clause 13.1 of IS 456, and for that you can see it is a dog-legged stair, so we go this way. This is the half landing, and then we move on this side. So you can see the geometry and you can identify X and Y, and accordingly you can calculate the horizontal effective span. So for that, these are the guidelines given. So effective span, depending upon X and Y and its combination, we can easily evaluate based on these 4 conditions. When we will take the example, we will come back to this point. So if X and Y both are less than 1 meter, then effective span is G plus X plus Y, or otherwise accordingly we have to design it, right? This is self-explanatory. It's not difficult. From the basic geometry, we have to identify X, Y and G, and then we have to check whether these conditions are satisfied, and accordingly we have to identify the effective span. Now, beyond this, there are some additional requirements that we have to keep in mind. You can see we have a starting point here, say at the ground level. So we start climbing, then this is the half landing, and then for the next floor, this is the landing. So when top and bottom risers are supported on beams spanning parallel to the risers, so we can have a beam here and we can have a beam here. Let us say mark it, and another beam here. Then obviously when we calculate the effective span, we have to consider the center line of this beam, and then accordingly we have to identify the effective span. Sometimes these slabs are supported on walls, then there are some additional requirements as you can see here. So accordingly we have to calculate the effective span, but for the time being, because mostly we deal with frames type structures where normally we have columns at the corners, in between columns we have beams, and then with the help of beams these stairs are supported. These are the most common dog-legged stair these days for high-rise buildings, and let us focus on that aspect where we have to consider this end beams and the center line of the beam. Otherwise, if it is on slab, we have to accordingly adjust the effective span length. Then comes the distribution of loading on the stair. As I told you earlier, the moment we consider these type of steps, we have to evaluate the dead load and its distribution over the inclined slab. So for that, the most important one is here, as you can see, and it reads, if the flight or landing is embedded into walls for a length greater than 110 millimeter and designed to span in the direction of flight, a 150 millimeter strip may be deducted. The span length may be reduced by deducting 110 millimeter from the effective span and increasing it by 75 millimeter for the design purpose, right? And as I already told you, we are going to consider end columns. Between columns we have beams, and accordingly we have to design. So in our case, we'll have no walls, but if there is wall, accordingly you can adjust the effective length and the loading on the stair. Now for loading on the stair, we have again dead load and live load. Now in case of dead load, we have waste slab contributing to the dead loads, then weight of each steps, as you can see here, weight of each step. So each step will contribute to the dead load. Then weight of flooring or finishing. So once we put the concrete here, then after that we have to put the flooring material here and here. We also provide some additional cover. And then when we calculate the dead load, we have to consider all of them, because all of them will contribute to the dead load of this slab spanning between two supports, say one here and two here. We'll see in a minute how we can calculate this dead loads. Beyond that, we have live load for a slab, and for live load again, we have IS 875 that provides us the live load that we should consider. And again, for residential buildings, we consider normally 3 kilonewton per meter square, and for public buildings where we have overcrowding, there we consider 5 kilonewton per meter square. Now, the question is how we can calculate the weight of waste slab. As you can see here, the dead load of the waste slab measured along the slope is converted into equivalent horizontal load by multiplying this factor. So what we do, we can consider the weight of the waste slab and then convert it using this factor. Then we must consider the weight of each step, that we can easily calculate from the geometry. So we know R and T, so we can calculate the volume, and we know the density of concrete, so we can calculate the weight of this step. Then for flooring, additional weights we need to consider as a UDL, and together they will contribute to the total dead load acting on the stair. So let us take an example. So in this case, we need to design a dog-legged stair. Stair hall size, as you can see, 3.2 meter by 4.8 meter. Vertical distance between two floors, 3.2 meter. Then first we need to design the dimension of the stair hall along with the number of steps. Then we have to design it with M20 concrete and Fe 415 steel. The staircase in our case is supported by 300 millimeter brick walls at the end of the landing. So you can see it is longitudinal spanning. So first we need to design this dog-legged stair. For that, what we do, the stair width we have to design. So the width of the stair hall is 3.2 meter. So this is 3.2 meter. Out of that, so what we can do, we can divide it into two flights, each of them 1.5 meter. So we'll have a 200 millimeter gap in between as stairwell. Then the total height is 3.2. So height of each flight will be 1.6, half of the height that we are going to cover. Then comes the stair design. So what we do, first assume the riser. So R is equal to 160. So the total height we need to cover is 3.2 meter. So we can calculate the number of risers, that is 3.2 by 0.16. So we will have 20 number of steps. So each flight will have 10 steps. So the first flight will have 10 and the second one will have 10. Obviously the number of tread is total number of steps we have minus 1. In this case it is 9. Now the moment we fix T, we can actually calculate this dimension, and then with the help of that we can design the stair hall completely. For that, again, let us propose T is equal to 250 millimeter. Then space required for 9 treads, 9 times this, that is 2250 millimeter. Therefore, the space left for passage, we have to provide the passage at the beginning and also in the form of mid landing, that we can calculate. So it is 1275 millimeter, right? So the geometry is fixed, as you can see here. So we have a passage here of size 1.275 meter. Then there are 9 number of steps per flight. As you can see, it starts from 1, it goes up to 9. Then we have a mid landing here. Its dimension is 1.275. For the timing it is same. It can be different also, but let us for the timing keep it same. And then we have another flight where the count starts from 12 and it goes up to 20. And if you see the other side, each flight will have a width of 1.5 meter with a stairwell in between of 0.2 meter. And we have also wall of 300 millimeter. So now let us first calculate the loads acting on the slab. So first is effective span. So we have the slab which is assumed to be supported at the base, then at the intermediate level, and then at the top level, right? And the width of the wall is 300 millimeter. So effective span is 4.8 meter, plus on the either side we have 300 millimeter support. So center line of the support, if we consider, we have to add 300 millimeter here. So we have 5.1 meter or 5100 millimeter. Then thickness of the waist slab. Normally we provide L effective by 20 from the serviceability criteria. So our thickness comes 250 millimeter. So let us provide a 260 millimeter thick slab for this stair. So weight per square meter, you can find out it is 0.26 times 1 times 25 kilonewton per meter cube. So effectively it is 6.5 kilonewton per meter, right? Then weight of the waist slab on plan per square meter plan area. So that is capital D, which is in our case 0.26, times this factor times 25. So effectively we have 7.8 0.72 kilonewton. And then dead weight of the steps that we can easily calculate. So that is here. So equivalent thickness, half of this riser, and then multiplied by the weight of plain concrete, which is 24 kilonewton per meter cube. So effectively we have 1.91 kilonewton. Remember, it is per square meter of plan area, right? Then what we do, total dead load of the waste slab. So we have the contribution from number 1, self weight of waste slab, then weight of steps, and then we have to provide a flooring. For that we consider 25 millimeter plain concrete. Then we have to provide the ceiling plaster. So we have to provide flooring here, then ceiling plaster here. For that again we add a lump sum weight, and then of course we'll have the railing. So we have to consider the weight of the railing. So this is the railing, and that again as a lump sum, as you can see here, it is 0.5 kilonewton. So the total dead load is the summation of all these, and for our problem we have 10.89 kilonewton per meter square. So next is we have a horizontally spanning beam in the longitudinal directions. We know the dimensions. So at the central portion we have this weight of steps, and that's why we have this weight that we have just evaluated. And at the beginning we have a passage to access the stair, and then we have half landing. For each of them we have the calculations here. So as you can see here, total dead load 7.26 kilonewton per meter square. Then on top of that we have to add the live load. So let us consider live load of 5 kilonewton per meter square. So that is the total load. Then factored load is 23.835, which is applied here. Then over the landing we have live load. So the total load on the landing is 7.26 plus 5, and we have to multiply with a factor of 1.5. So it is 18.39. So you can see at the two landings we have 18.39 kilonewton per meter. Now this is a simply supported beam. So for this simply supported beam we can find out the reactions. So we have reactions at the end A and at the end B. So RA is 53.02 kilonewton. RB is also 53.02 kilonewton, because this is a symmetric structure with symmetric loading. Then we can find out the maximum bending moment which will occur at the middle. So maximum bending moment is 71.967 kilonewton meter. Then once we get the maximum bending moment, we can find out the depth. This is familiar to you. So you can find out small d, or effective depth, which is square root of m by r times b. Now, depending upon the type of concrete and steel that we use, accordingly we can design. So you know how to calculate this capital R. We have already done that earlier. So effectively what we get, our desired depth is 162 millimeter. So we provide 20 millimeter clear cover and design with 16 bars. So effectively we have to provide 172 millimeter. And then the overall depth you can calculate. Then overall depth will be 162 plus 20 plus 16 by 2, which is 190, and that is less than the depth we have provided, which is 260 if you recall. So the design is okay. Next is we have to find out the AST. Again, this expression is common to us. We have already used this for beam design and slab design. So AST from the type of concrete and steel we use is 1394 millimeter square. So we have to provide this much of steel for the safe design. Now, again, the number of bars that we have to calculate. So we provide 16 millimeter diameter bars, each having 201 millimeter square area. So we can find out the spacing, which is 144 millimeter center to center. So what we do, we provide 16 5 bar with 140 center to center distance. Then that is the main bar. So we have to provide some distribution reinforcement in the perpendicular direction. So for that, we provide 0.15% of the total cross-sectional area. So cross-sectional area per meter is 260 into 1000. 0.15% of that, which is 390 millimeter square. So if we provide 10 meter diameter bar, we can find out the spacing the same way we have done for the main bars. So in this case, it is 201 millimeter. So we can provide 10 millimeter diameter bar at 200 center to center. So that completes the design. The next step is actually to find out the development length for checking, and we have to detail it out. As you can see here, the development length is 752 millimeter. So we provide 800 millimeter length bars at points where LD is required. So at the ends, so accordingly we have to design. And then you can see here 200 millimeter thick slab. Then we have the main rebars, as you can see, 16 5 140 center to center, and then distribution bars 10 5 200 center to center, right? And you can see here the amount of development length provided for the bars. Okay, so that completes the design of a dog-legged stair supported by walls at the end, and this is a longitudinal spanning dog-legged stair. So go through this design guidelines and examples. Just practice it. If you have any doubt, do let us know. We'll clear your doubt. Thank you very much.